Ever wondered how Netflix recommends movies you might like, or how your email filters spam? Welcome to the intriguing world of machine learning. This technology, often abbreviated as ML, is an integral part of our daily lives, even if we don't always notice it. From personalized marketing to fraud detection, from image recognition to stock market forecasting, machine learning algorithms are constantly working behind the scenes, making sense of vast amounts of data and assisting us in making informed decisions. In this video, we'll delve deep into the different types of machine learning, categorized by learning strategy, task or problem, and approach or technique. We'll uncover the fascinating strategies that machines employ to learn from data, solve complex problems, and even make decisions. Ready to take your first steps into this fascinating world? Let's begin with how machine learning is categorized by learning strategy. Imagine a teacher guiding a student with correct answers during a lesson. That's supervised learning in a nutshell. It's one of the most common frameworks of machine learning, where our model, or student if you will, learns from an existing labeled dataset. The idea here is to provide the model with the correct answers during its training phase. Consider this. Let's say we want to predict whether an email is spam or not. We would use a dataset where each email is already labeled as either spam or not spam. This is an example of a classification problem, one of the key players in supervised learning. On the other hand, if we're trying to predict a continuous variable, like the price of a house based on its features, we're dealing with another supervised learning star called regression. So, with supervised learning, the machine becomes our well-trained student. But what if the machine has to learn without a teacher? Now picture a student learning independently, without any guidance. Welcome to unsupervised learning. In the realm of machine learning, unsupervised learning is akin to self-discovery. It's like a detective trying to solve a mystery without any clues, using patterns, correlations, and structures hidden in the data to make sense of it all. Take clustering, for instance. It's like organizing a wardrobe without tags, grouping similar items together based on their properties, such as color, size, or style. Imagine an algorithm sorting through heaps of data, grouping similar data points together just like clothes in your wardrobe. Then there's association, which helps us find relationships between variables in large data sets. It's like observing that people who buy bread often buy butter too. Finally, we have dimensionality reduction, simplifying complex data without losing its essence. It's like condensing a lengthy novel into a brief yet insightful summary. Unsupervised learning shows us that machines can learn and adapt without any guidance. But what if we combine the best of both worlds? What happens when you blend labeled and unlabeled data or introduce a reward system? You get semi-supervised and reinforcement learning. Semi-supervised learning is like a hybrid vehicle, combining the best of both worlds. It learns from a small amount of labeled data, the ones with the correct answers, and a large amount of unlabeled data, the ones left to its own devices. Why would we do this? Think about it. Labeling data can be a strenuous task, often requiring experts and a lot of time. So, when labeling data is expensive or time-consuming, semi-supervised learning steps up to the plate. It's a cost-effective, efficient way of teaching our models. Now, let's take a turn and talk about reinforcement learning. It's like training a pet. When your dog does a trick correctly, you give it a treat. But if it messes up, well, no treat. Similarly, in reinforcement learning, a model learns to make decisions by performing actions and receiving feedback. That feedback comes in the form of rewards or penalties. If the model makes a good decision, it receives a reward. If it makes a poor decision, it receives a penalty. Digging a little deeper, we find key concepts like Q-learning and policy gradient methods. Q-learning is a value-based learning algorithm in reinforcement learning. It calculates what action to take based on an action-value function that determines the value of being in a certain state and taking a certain action at that state. Policy gradient methods, on the other hand, directly optimize the policy function instead of the value function. They are a type of reinforcement learning methods that rely on improving the policy of the agent based on the gradient ascent algorithm. And then there's deep reinforcement learning, which combines deep learning and reinforcement learning principles to create efficient algorithms that can be applied to very complex tasks, like playing a video game or driving a car autonomously. From learning with a mix of data to learning from rewards and penalties, machine learning sure has diverse strategies, but we're just getting started. Can data supervise itself, or can labels be associated with groups instead of individuals? Enter self-supervised and multi-instance learning. In the realm of machine learning, self-supervised learning is a fascinating strategy. Unlike supervised learning, where labels are provided, and unsupervised learning, where no guidance is given, self-supervised learning finds a middle ground. Here, the data itself becomes the supervisor. Wondering how? Well, it involves creating auxiliary tasks that predict one part of the data from the other parts. For example, given a sentence with a missing word, the model is trained to predict the missing word, using the surrounding words as context. This way, the model learns to understand the data better, without needing external labels. Now, let's shift gears and talk about multi-instance learning. It's a variant of supervised learning where labels are not associated with individual instances, but with groups of instances. Picture this. You're given a bag of apples and told that the bag contains at least one ripe apple. You don't know which apple is ripe, but you know that at least one is. That's the essence of multi-instance learning. The label applies to the entire bag, not the individual apple. This approach is particularly useful in scenarios where it's hard to label individual instances, but relatively easy to label groups. For instance, in medical imaging, it might be challenging to label every pixel in an image as tumor or not tumor, but it's much easier to label the entire image as contains tumor or does not contain tumor. So, in self-supervised learning, the data itself provides the supervision, and in multi-instance learning, labels are associated with groups of instances rather than individuals. These strategies highlight the flexibility and adaptability of machine learning, accommodating different data types and scenarios. As we've seen, the strategies for learning are multifaceted. Now let's discuss how these strategies are applied to solve tasks or problems. From recognizing images to predicting house prices, machine learning solves a wide range of tasks and problems. It's like a Swiss Army knife in the world of data, ready to tackle a multitude of challenges with its different tools. Let's delve into some of these tasks and problems, shall we? First off, we have classification. This is like the sorting hat in Harry Potter, but instead of sorting students into houses, we're assigning categories to data. Spam detection in your email, that's a classification job. Image recognition, also classification. Machine learning is constantly categorizing data behind the scenes. Next up is regression. Now, regression isn't about going backward, it's about predicting a continuous quantity. For example, forecasting the stock market or predicting house prices. It's all about looking at patterns and trends in data and making educated guesses about what comes next. Then there's clustering. This is like herding similar instances into their own specific groups. In the world of marketing, it's used for customer segmentation. In biology, it's used for gene sequence analysis. Clustering helps to make sense of vast amounts of data by grouping similar items together. Anomaly detection is another important task. This is like a detective finding clues that don't fit the usual pattern. It's used in fraud detection and network security. Anomaly detection helps identify unusual patterns that could indicate a problem. Dimensionality reduction is a bit like spring cleaning for data. It's about reducing the number of variables under consideration, making the data more manageable and easier to understand. It's used for feature selection and extraction. And finally, there are recommendation systems. Ever wondered how Netflix always knows what movie you'd like to watch next? That's a recommendation system at work, suggesting products or services based on your behavior and preferences. Machine learning proves to be a versatile tool in problem solving. But how does it achieve this? Let's explore the different approaches or techniques. The secret to machine learning's problem-solving prowess lies in its diverse approaches and techniques. Deep learning, a subset of machine learning, is like the superhero of the machine learning realm. It uses neural networks with many layers to handle vast amounts of unstructured data. These layers enable the model to learn complex patterns and make accurate predictions. It's like peeling an onion. The more layers you peel, the more you uncover. Then we have transfer learning, a clever approach that applies knowledge gained from solving one problem to a different but related problem. Imagine you've learned to ride a bicycle. You can then apply that skill to ride a motorcycle or even a unicycle, with some tweaks, of course. That's what transfer learning does, making it a common choice in deep learning applications. Next up is ensemble learning, the democracy of machine learning approaches. Instead of relying on a single model, it combines the predictions of multiple models to produce a single, more accurate prediction. It's like asking a group of experts for their opinions and then making a final decision based on their inputs. Examples include random forests and gradient boosting machines, both of which combine multiple decision trees to make more accurate predictions. Active learning, on the other hand, is like a picky eater. It's an approach where the algorithm selects the samples from which it learns. This makes it efficient in situations where labeled data is scarce or expensive to obtain. It's like going to a buffet and choosing only the dishes you know you'll enjoy, instead of trying everything and risking indigestion. Online learning is the epitome of adaptability. These models learn incrementally by continuously updating the model as new data arrives. It's like navigating a new city without a map. You learn the routes and landmarks as you go, constantly updating your mental map of the city. Finally, we have federated learning, a machine learning approach where the model is trained across multiple decentralized devices or servers holding local data samples without exchanging them. It's like a group project where each member works on a part of the project independently, and then their individual work is combined to create the final output. This approach ensures privacy and reduces the need for central data collection. These innovative techniques make machine learning a powerful tool for processing and understanding vast amounts of data. Each approach has its strengths and is best suited to specific types of tasks and problems. The beauty of machine learning lies in its adaptability and the variety of techniques it offers to tackle different challenges. As we continue to advance in this field, who knows what new approaches we might uncover in the future? But one thing's for sure, the machine learning journey is far from over. It's just getting started. With these strategies, tasks, and techniques, machine learning is shaping the world as we know it. Machine learning, a pivotal branch of artificial intelligence, is already leaving an indelible mark across numerous sectors. It's like an invisible thread weaving through the fabric of our daily lives, often unnoticed, yet incredibly transformative. In healthcare, machine learning algorithms are revolutionizing diagnostics and treatment plans. They sift through vast repositories of medical data, recognizing patterns that are often too subtle for the human eye, enabling early detection of diseases and personalized treatment strategies. The finance sector is also harnessing the power of machine learning. Algorithms help detect fraudulent transactions in real time, saving companies billions each year. In addition, it's reshaping investment strategies, with robo-advisors providing personalized investment advice based on an individual's financial goals and risk tolerance. In the realm of entertainment, recommendation engines are using machine learning to curate personalized content, transforming how we discover new music, movies, and television shows. It's like having a personal concierge service at your fingertips, one that knows your preferences better than you do. And then there's the transportation industry. Machine learning is the driving force behind autonomous vehicles. It's teaching cars how to navigate complex environments, handle unexpected situations, and even learn from their mistakes, bringing us closer to a future where self-driving cars are the norm. But this is just the beginning. The future of machine learning holds limitless possibilities. Imagine a world where personalized education is a reality, where learning systems adapt to each student's unique learning style and pace. Think of predictive policing, where law enforcement agencies can anticipate crime hotspots and deploy resources proactively. Picture a future where machine learning can predict climate trends with pinpoint accuracy, enabling us to take proactive measures to mitigate the effects of climate change. In the realm of business, machine learning could revolutionize decision-making processes. By analyzing vast amounts of data, businesses could anticipate market trends, optimize supply chains, and make strategic decisions with unparalleled precision. And let's not forget about the potential advancements in the realm of natural language processing. We can expect to see intelligent virtual assistants that can understand and respond to natural language with the same nuance and context as a human being. However, with great power comes great responsibility. As we continue to develop and deploy machine learning systems, we must also address the ethical implications. Issues like privacy, data security, and algorithmic bias need to be at the forefront of our considerations. Ensuring that these systems are transparent, fair, and accountable is paramount. With every passing day, machine learning is becoming more intertwined with our lives, changing the way we work, play, and interact with the world around us. It's a thrilling journey of discovery, innovation, and transformation. As we continue to harness the power of machine learning, who knows what incredible innovations the future holds?